In this video, I want to tell you a little bit more about the FIR-filter designer we have in the program. FIR stands for Finite Impulse Response. And with this designer, 4 types of filters can be calculated. What you're calculating are the filter depths of the digital filter. We have a low pass, band pass design, high pass design, and a band reject, band stop filter design. If you click on each individual design, you can see here in this area that all these parameters are set. For example, if you click on low pass, frequency A is going to be 0 Hz. Frequency B in this case is a quarter of the sample frequency. If you click on high pass, the high pass frequency is here, and the maximum frequency of this filter is half of the sample frequency, so this is fulfilling the Nyquist criterion. This is the number of points of the filter. So if you change this number here, you can see that the quality of the filter is strongly depending on the number of points you're using, sample frequency, and the attenuation levels. Let's say, let me change this, for example, to 20 dB. You can see here that this filter here is filtering much less than if we have a 90 dB filter. In this box here, you see all the filter depths that you need to implement in your design. By the way, the design is a Kaiser-Besser design. And these filter depths here are also represented here, which is the impulse response. So this is time domain, and this is the impulse response of the filter here. And this is the T0 moment. If you look here, let's bring back the number of points. So you can see here that this, let me see, we are 37 points, so somewhere in the middle is here. And here you can see that sample number, let me see here, sample number 18, which is the sample in the middle, is 0.5. You can see here it's 0.5. And the 2 taps left and right are minus 0.314. So the taps here, you can see them here as well. It's actually the time domain impulse response of the filter. Here you see the frequency response, and the nice thing is, as soon as you change the number of points here, or if you change the sampling rate, there is an immediate response of the calculator to the things that you would like to change. So let's go back to 44.1. Let's select the low pass filter and type in here, for example, 2300 Hz, and here is your filter. You see here the impulse response of the filter in the time domain. All right, so let's have a closer look at some of the items here. So FA, FB, in case of a low pass, FA is always 0. In case of a high pass, FB is always half of the sampling frequency, because you cannot go higher in frequency. Band pass, then in that case, there is a selection here of 5 to 6 kilohertz. Of course, you can change this figure here to, for example, 10 kilohertz, and then your filter is much wider. If you take a higher number of points, you see the filter gets sharper. And with this same frequency set, you can change between band pass and band reject. So let's say if we zoom in here, so let's do this. You can see here nicely the frequency response of the filter. How is the zooming working? You just select an area on the graph, what you would like to see more closer. And then you do this. You just unzooming, unzoom, or all zoom pan. So that gives you the original graph. So what you see here is the S21 of the filter. If you need some more about filtering, click just on the Wikipedia link and it brings you with the internal browser form to the Wikipedia page dealing about filters. So this is what it can do. Thank you very much for your attention.